here, so.
Archiving started.
Okay, so now we're recording. We're live now.
But, yeah, so anybody's in my class, make sure you, there's a signature sheet up there. That's what the record is. Is that your signature sheet up there?
Well, that's the signature sheet, and then I'll distribute it to all the instructors.
Okay. So you want me to start?
Yes, you can go ahead and get started.
So, the Lunar Reconnaissance Orbiter, LRO, is orbiting the moon, and it has been for about a year and a half. And this is the conception of it orbiting the moon. But it's being used to collect all kinds of data about the moon. It's called the Lunar Reconnaissance Orbiter because when it was built and launched, the original plan was to have a permanently manned lunar base eventually. And this was to be doing reconnaissance for that base. Now it looks like the base won't be built. Although there's about 5 other countries that want to build lunar bases. So, I mean, this information will be very valuable to anybody that builds a lunar base, whether it's NASA or one of the other space agencies. The subtitle here, Exploring a Planet on the Cheap. Some of you are probably thinking, well, Lunar is really a planet, right? It's a moon. A planet orbits a star, a moon orbits a planet. That's true, but I use that word for a couple of reasons. For one thing, the Earth's moon is a big moon, planet size. And for another thing, the instruments that are on LRO are also on other probes orbiting other planets or on their way to other planets. For example, the Mars Odyssey orbiter that's been there since 2001 has some of these same kinds of instruments to study the surface. And the Messenger probe that will pull into orbit around Mercury in a couple of months has some of these same types of instruments. And the Dawn probe that's on its way to study the dwarf planet Ceres and the asteroid Vesta. Some of these same types of instruments are on all those things. And so this is part of the reason I wanted to talk about this. It's a good description of how you study a planet from orbit without having to land on the surface. And the reason it's exploring a planet on the cheap is because landing on the surface is a lot more complicated. Okay, can you flip that ahead one? This is a photograph from the surface of the moon, and this right here is the lunar lander. This was taken by one of the Apollo 17 astronauts. That was the last manned mission on the moon in '72. And this photograph is taken several miles from the lander. It was done with a telescopic lens. So they were a long way from their lander. They had a lunar rover, a little car that they went around in. And I like it because you can see how small these lunar mountains in the background. Apollo was a truly ambitious effort. Can you go ahead with that? You can get an idea of what it takes to send a manned mission to the moon by looking at the rocket that was used. This was the type of rocket used for every one of the Apollo missions. It's the Saturn V, nearly 400 feet high, and it liftoff weighed 3,400 tons. That's about the weight of a freight train, one of these container trains that goes blasting through downtown Clarkston. Probably weighed about that much. Imagine lifting that up off the ground using rocket engines. It gives you an idea of the scale of the effort of Apollo to send people to the moon. So sending people to the moon is a really, really difficult thing. And they used to do reconnaissance beforehand because it's a lot simpler to send a small probe than an entire manned spacecraft. So 2 spacecraft in this case. Okay, go ahead. This is a photograph of the moon taken by the Apollo 17 astronauts when they were leaving. They just done the burn to get out of lunar orbit and come back to the Earth. And you can see...
I'm sorry, I tried to do something that didn't work.
Okay. You can see the moon has all these impact craters, all these round things that are impact craters. The moon has essentially no atmosphere and very little internal activity, so it doesn't erase features on its surface like Earth does. Earth has been impacted as much as the moon, more so. But Earth has weather and tectonic and volcanic activity, and so most of the features on the surface of Earth that have been put there by things like impacts from space have been erased over time. But the moon, has preserved many of these extremely old features for most of the history of the solar system, and so it serves as a record of impact activity in the solar system, which is a record of what has been orbiting the sun for the history of the solar system. That's one of the reasons that the moon is a valuable thing to study, because of the fact that it preserves this record, whereas Earth does not. Go ahead. Another interesting thing about the moon is its size. Here's Earth, there's Earth's moon, and here's some of the other large moons of the solar system. These four orbit Jupiter. This one's orbiting Saturn, that one's orbiting Neptune. Saturn and Uranus also have some moons that are sometimes called medium-sized moons. And then all of the big planets, Jupiter, Saturn, Uranus, Neptune, have dozens of teeny moons that are called small moons. And Mars has two small moons. I think those are actually exaggerated in size. They're nothing like Earth's moon. But you can see Earth's moon is comparable in size to the largest moons of the solar system. And go to the next slide. And that, even though this is Earth right here, these are the big planets that have most of the moons in the solar system. So Earth has a big moon, but it's a small planet. So Earth's moon is unusually large compared to the Earth, as moons go. And because of that, Earth's moon affects Earth dynamically through its gravity. For example, the ocean tide. If you go down to Tybee Island, sit on the beach for more than a couple hours, you notice the tide change. That's caused by the moon. And Earth's motion in space is affected by the moon. And some of the ways that it's affected are thought to be important for the stabilization of conditions on the surface of the Earth to make it habitable. For example, the moon's presence is thought to have stabilized the orientation of Earth's rotation axis over the long history of life. And that's what allowed life to proliferate over this long history of life. And so without the moon, we most likely wouldn't be here. So the moon is not just an ornament in our sky, it's actually part of the dynamic system of Earth. You can think of it as a single system, the Earth-Moon system. So it's an important object to us. It's not just some other place in the solar system. It's actually part of Earth's system. Go ahead. And the way that it's formed is interesting too. This is a freeze frame of a computer simulation of an object about a tenth the mass of the Earth. That's about the size of Mars, smashing into the Earth in the very early history of the solar system, just after the Earth formed. And if you run this simulation ahead, some of this material that's been blown off comes back together by gravity and forms an object very much like the moon. And these types of simulations are very successful in producing a system that's like the Earth-Moon system in the way that they're moving and in their composition. And this is the only plausible mechanism that astronomers know about for the origin of the moon. According to what we know about how planetary systems form, this is the only thing that seems to have the capability of forming this large moon orbiting a small planet. So, and nobody knows, of course, how common this process is in the early history of a planetary system. Is it a really rare event for another planet to smack into one and make a moon? And of course, that's important to know if we're to think about where there's life elsewhere in the galaxy or in the universe. The most logical place to look would be a system that's like the Earth-Moon system out there. We don't know how common they are. There is another reason for studying the moon, because we want to understand this process that formed it better. Okay, go ahead. Okay, here's LRO. This is a solar panel powered, all the electrically powered things are powered by solar power. And here's an antenna. The people on the ground that run the thing have to be able to communicate with it, so they communicate through this antenna. It has a propulsion system, little rocket engines that are used to adjust its orbit. They were also used to insert it into orbit around the moon when it first got there a year and a half ago. Okay, next. This is the other side where you can see the sign of the instruments. The science instruments are all labeled by their acronyms, and I'll talk about each of these. But there are 8 of them, 8 main science instruments on board. Go ahead. Here are the instruments. These 4 are all basically cameras of various types. This is a wide-angle camera that's being used to make a comprehensive photographic survey of the entire surface of the moon. LRO is orbiting, polar orbiting. So it's the north pole and south pole of the moon. It's orbiting like this, and so as the moon rotates and it orbits, it can scan over, eventually scan over the entire surface. That's the way of doing that. You see. So that's what that camera is for, making a complete photographic survey. And then there's this narrow angle camera. Yeah. There's your moonquake there. These are narrow angle cameras, telescopes, for taking high resolution images of certain places of great interest. There isn't enough time in the whole mission to photograph the entire surface at high resolution. But places of greater interest, like the lunar geologist may say, well, there's a crater over here and we'd like to get a higher resolution image of that because we want to know the processes that have been going on since its impact. And also for potential landing sites, if they want to have lunar landing missions, you want to know if there's big rocks strewn all over the place for land for them. So I'll show you some images from that that are really things like this on the surface of the moon, like these images. It's much better resolution than anything ever before. This is an infrared camera, and I'll show you what that's for. This is a camera for taking images in extremely low light. I'll explain what that is. This is a neutron detector, and I'll explain why neutrons are coming up from the surface of the moon and why it's interesting to look at them. This instrument basically measures the radiation environment because for manned missions, you want to know what sort of radiation people are going to be exposed to. When the Apollo astronauts went to the moon, they were there for at most 3 days. Now, with a lunar base, people might stay there for 6 months or a year. So the radiation environment is much more important because they're bathed in this radiation for a long period of time. They want to know what they need to protect against if they're going to build a lunar base on the surface. So that's what that's for. This is an altimeter. I'll talk about that instrument first. And this is a sort of a test instrument. It's not a full-blown. They're demonstrating this type of instrument on LRO. It's a mapper. It maps the surface using radar. But I'm not sure if they've learned anything just from this instrument, except the performance of this type of instrument. Okay, great. Here's LRO in the clean room, and it's being prepared to be loaded on the rocket to launch it in space. And again, the instruments are labeled. This is the person in a surgical clean suit. But most of these covers that are on the pieces are taken off. They're there for during the assembly. But some of it is actually insulation on there. The environment in space, it's difficult to maintain your temperature in space. You're either too hot or too cold. When you're in the sun, you're too hot, and when you're not in the sun, you're too cold. So there's a lot of thermal insulation around stuff on the good. Okay, here's the first instrument I want to talk about. It's the Lunar Orbiter Laser Altimeter, LOLA. And it has a powerful laser in here. It shoots a pulse. As LRO orbits the moon, these pulses are shot down towards the surface. And the laser light goes down, scatters off the surface, and some of that scattered light happens to go back up to the probe and is received in this gun. And the amount of time that it takes for the pulse to go down the surface and back up is used to determine the distance from the surface to within a couple of inches. And so it's an altimeter because it measures its altitude that way. And do that 1 billion times, and you build up a topographical map of the surface of the moon. So that's LOLA's function in life, to make a topographical map of the surface of the moon. That's very helpful to the planetary scientists that studies the formed on the moon, and also for planning for lunar landing mission. So it measures altitude.
Excuse me, I accidentally clicked.
Is it? Okay. It measures altitude. It can also measure some information about surface roughness, because as the pulse goes down, it spreads out and gets over a wide area, and the roughness of the surface affects the reflected pulse that comes back up, so they can infer some things about the roughness of the surface in there. And also surface brightness. The lighter in color it is, the more light is reflected back. One of the reasons they wanted that capability is because one of the things they're looking for is water ice on the surface, because water is a very valuable resource if you're building a lunar base. And of course, water ice, frost is real light in color, so it's highly reflective. So that was one of the things they're hoping to detect with that. I'm not sure they have, but there's definitely water ice there. One of the reasons, well, the reason they want to find water is water is, used for a lot of things on a lunar base. You can drink it, you can bathe in it, you can use it as a coolant and a solvent, and you can also use electricity to separate H2O into hydrogen and oxygen, and then you can use it as rocket propellant. And you need rocket propellant to get off the surface of the moon back up into orbit. And also, if you want to move around the moon, say they're at a lunar base and they want to go on some research excursion 500 miles away, you're going to fly, and the only way to fly on the moon is with rockets. And so it provides you with rocket propellant. And that's that much rocket propellant you don't have to bring from the surface of the Earth. And that saves a lot of resources, because taking things off the Earth and taking them to the moon is really expensive. So water is one of the primary sources that they want to find with LRO, and they found a lot of it. Good. Okay, so here's the moon as seen from Earth. Go one more. And this is LRO's LOLA's altitude map. Blue designates low altitude, and red is high altitude, and the other colors are in between that. So go back again to see this one. You can see these dark regions that are easily visible with the naked eye from the Earth. Those are the Maria, that's plural for Mare, M-A-R-E. Now go ahead. Those, you can see, are relatively low altitude and relatively constant altitude. In other words, flat. Those are the low-lying flat plains. They're big impact basins, very, very ancient impact basins that were filled up later by tectonic, mostly volcanic activity, so they're smooth and flat because of lava that filled them. The moon is long since volcanically dead, but early on it had volcanic activity which put a lot of lava on the surface. And then some of the high altitude regions are mountainous. They're literally called the highlands. They're very mountainous and rough. You can see some of the lowest altitude places are the bottom of these deep impact craters, like this one is called Copernicus. And if they do any more landing missions, they do some manned landing missions, one of the places they'll probably land is near one of these, because when that impact occurs, it excavates rock up from miles underneath the surface. And geologists always want to look at rocks from all depths, right? So you go there, or scan it around here for dozens of square miles of all kinds of rocks that were excavated up during that impact. In fact, one of the canceled Apollo missions was going to land either in that crater or somewhere around it. There were 3 more Apollo missions that were canceled by our geniuses in Washington. And they were going to, that's exactly what they were going to do. Okay, go ahead. Here's both sides of the moon, the far side and the near side. The moon is in synchronous rotation. So, thank you. So I'm trying to get that. Okay, here's the side that faces the Earth. So as I go around, pretend my head is the Earth. This is the way the moon orbits the Earth. The same side always faces the Earth. Now, to me, it looks like it's not rotating, but it is rotating once every time it goes around. And the reason that it going around like this is it's been locked into that situation by the gravity of the Earth. That's synchronous rotation. So the same side always faces us, the same side always faces away from us. And, okay, so this is the near side, that's the far side. And you can see they're quite different in terms of altitude. For one thing, the altitude extremes are more extreme on the far side. There's high altitude places and low altitude places. This huge basin is thought to be the result of very early, very large impact. And in this high altitude region can actually be a result of the same impact. Another difference is on the far side, you don't see these big, broad, smooth plains. You don't see these basalt-covered plains. There are none of those big dark regions, but very few of those big dark regions on the far side. So this altitude information is very valuable to people who study the processes that make the features on the surface of the moon, and valuable in planning future missions. Okay, go ahead. One thing that was done with the LOLA data, they did a survey of all the large craters on the surface of the moon. I think it was everything larger than 20 kilometers in diameter. So you can see these circles that have been put on the LOLA map. Each of those is an identified impact crater. And the reason to do that is a combination of the count of the craters as a function of size and the ages of each crater. It's complicated to find the age of a crater, but it's a complex process. But knowing the ages and the numbers of them, they can say something about the impact history of the solar system. And one of the things they found from looking at this data from the LOLA instrument is that there were a disproportionately larger number of large impacts early in the history of the solar system. Right now, I mean, there's still objects impacting the moon, mostly little, and as you go to larger and larger impacts, there's fewer and fewer of them. That's always been the case. There's always more smaller impacts, fewer larger impacts, but early in the history of the solar system, there was a greater impact rate overall, plus there were disproportionately more of the larger impacts. It's one of the things they concluded from looking at this information. And that has some implications about what was going on in the solar system. I'm not sure how the arguments work, but they say that the big planets, the Jovian planets, may have been interacting with the asteroid belt and dislodging objects from there that were going into the inner solar system and impacting. So it tells us something about the history of the dynamics of the solar system, because the moon preserves this information. All right. Now, the lunar base, if lunar bases are built there, they would probably be built at one of the lunar poles. And to understand why, you need to understand the motion of the Earth. Now you can make it off. This is, okay, in this diagram, the Earth's orbital plane is horizontal. So horizontal plane coming out of the screen. I guess this is supposed to be the sun back there in the plane, way in the background. And downloaded this figure off the web. But anyway, the Earth's orbital plane is horizontal. And most of you probably know that the Earth's rotation axis is tilted with respect to its orbital axis by 23.5 degrees. And that's what gives us the seasons, right? We're going on to winter now. Okay, this is the sun. We're going on to winter because the axis is, we're in the northern hemisphere. And we're getting to where the northern hemisphere is tilted away from the sun, so the light strikes at a lower angle, so it's less concentrated on the surface, and that's why it's colder now. So Earth's axis is tilted about 23.5 degrees. The moon's orbital axis is tilted less than that, only about 5 degrees from the Earth's orbital axis, which means the moon orbits in a plane that is only about 5 degrees different from the Earth's orbital plane. And the moon's rotation axis is tilted even less, only about 1.5 degrees from the Earth's orbital axis. And that means that the light that shines from the sun, which is much farther away than the moon, shines almost directly down on the equator. As the moon rotates, light is always coming straight down on the equator, and then almost horizontal at the poles, right? All the time. And that means if the light is shining horizontally at the poles, that means that if there's canyons or deep craters there, the bottoms of them are never going to be in sunlight. Do you see why? Because it's horizontal, so it's never going to go down in these deep craters. So since they're never in sunlight, they're going to be very cold. And since they're cold, they can preserve water ice, which is what we're looking for. So, you can go ahead, Mom. This is not a photograph. It's a computer simulation of the cumulative solar illumination on the craters at the south pole of the moon. Those dashed white lines are latitude lines, right? So the south pole is right in the center here. But what they did is they took data from the LOLA topographical map and used it to make a computer simulation of the total illumination by the sun, the cumulative illumination by the sun on this area. And so the lightest regions are the places that have gotten the greatest cumulative solar illumination over this 100 years. And then you can see there's a whole bunch of places that are completely black, but there's been no light at all for that whole century. And so those are the places, and you can see it at the bottom of these craters mostly. Now, so that's a valuable thing for a base. The other valuable thing about the poles is the tips of these craters and the tops of mountains aren't nearly constant sunlight. The bottoms of the craters are in constant darkness. The tips are in nearly constant sunlight. And so if you have a big mountain here, you're going to get sunlight, and even though the moon rotates, it's never going to be out of sunlight, right? Whereas at the equator, it takes about a month for the moon to orbit once. So you have 2 weeks of day and 2 weeks of night. Well, constant sunlight is helpful for a lunar base too, because that's how you make electrical power. And you can't be, if you have a manned lunar base, you can't be out of power for 2 weeks at a time. So the pink dots mark locations that are nearly constant sunlight. And so, like for instance, right here, there's a location where there's several pink dots, several places you could have solar panels, and then right next door is a deep crater where you might find out. So the poles are logical places for a lunar base for those reasons. Okay, good. This is also not a photograph. It's a temperature map made by another instrument, which I'll talk about now. And you can see the temperature scale down here. This is on the Kelvin temperature scale. 0 on the Kelvin scale is absolute 0, the coldest possible temperature, which is like minus 460 Fahrenheit. And you can see it says 300 Kelvin. So some of these bright places are about 300 Kelvin. That's about the temperature of this room. So these spots up top are temperature of this room, and then the coldest places are way down, close to Kelvin 0. There are spots that are below 30 Kelvin in some of these craters. And that is the coldest temperature ever recorded on any surface in the solar system. That's not to say there aren't colder places somewhere, but it's the coldest ever measured. And colder than people thought it would be. So that's plenty cold enough to preserve life. Okay, go ahead. These are just more extensive maps of temperature, and it shows daytime temperatures and nighttime temperatures. And you can see that the bottoms of these craters remain cold through daytime and nighttime. The appearance of this map is because LRO is orbiting in a polar orbit, and this is rotating, it makes strips of temperature measurements that put together something from that look funny like that. Okay, go ahead. This is the instrument that measures the temperature. It's an infrared camera. And the way it measures temperature, it's actually rather like the way the human visual system detect color. There are 4 different kinds of light-sensitive neurons in the back of our retina. There are the rods, which are sensitive across the whole visible part of the spectrum. And then there are 3 types of cones. One type is sensitive to the low-frequency part of the spectrum, one the mid-range and one the high-frequency. And the reason these colors look different to us is because the balance of how each of those cones is stimulated by the light reflecting off. Like this is red. Red light is how we perceive the lower frequency light in the visible part of the spectrum. So, I mean, there may be high frequency light here, but there's a greater fraction of the lower frequency. And the relative balance of how it stimulates those 3 different types of cones is what gives these things the different colors. So color is really nothing but our visual system's way of interpreting the relative brightness in different parts of the spectrum. So it gives us some kind of spectral sensitivity. And the way this, I like to think of it as just infrared color vision. All objects emit light all the time. You and I are emitting infrared radiation, so is the surface of the moon. And so the way it takes temperature is it looks at the light that's being emitted, and it looks at it in the different parts of the spectrum. You can switch a light off and advance it one. This shows there's actually 9. Like we have 3 types of cones. There are 9 filters on these cameras that let in different parts of the infrared spectrum. So, like filter A3, for example, it's a little bit lets in a little bit at 7.4 microns, and then it's the most in most at 7.6 or something. And then not so much, above 8 microns. And the A4 filter is this much, and so forth. 2 of the filters are not shown here, but this is what they call the band path of these different filters. Now, these 4 filters, these are the longer wavelengths. You take a picture of an object, the different patches of surface on the object are going to be the balance of brightness between these 4 filters is going to depend almost completely on the temperature of the object. The warmer an object is, the faster it emits at all wavelengths, but the relative amount of the different wavelengths also depends on temperature. So by making an image of the surface, it's essentially 4 images of the surface, and these are like the different colors, right? So that the different balance of these parts of the spectrum tell them the temperature. These, as it turns out, these wavelengths, the relative amounts that are coming out of an area depend not only on the temperature, also on the composition. And so they can get composition information by looking at the balance of these. Advance it one more. This shows the emission spectra of these various kinds of minerals in that part of the spectrum. And you can see they're different. And these are, red X is supposed to be the brightness in each of those different filters. And you can see it's a different ratios of brightness of the 3 filters for all these different minerals. Now, when you look at rocks on the surface of the moon, you're never going to see pure minerals. You're never going to see just quartz or just a microcline or just lead residue. It's always going to be a mix. But what they do is they get the information and kind of model it to see what mix of the minerals best fits. So you can get some mineralogical information about the surface. So this instrument is making a temperature map of the surface and also a mineralogical map. So the geologists have information about both those things. Good. Now, okay, so you've measured the temperature of the bottom of these craters and it's very cold. Is there any way to tell if the ice is actually there. Well, a number of instruments on board LRO are designed for that. And in fact, when LRO was launched, another probe launched with it. And that probe's sole purpose in life was to see if there's ice in one particular spot in one particular crater. And that other probe was called LRO. This is the rocket that launched it. It's an Atlas V rocket, much smaller than the Saturn V. This is the Atlas booster, all broken down in part. The Atlas booster that got it up to a certain speed and altitude and then ran out of propellant and dropped off. Here's the Centaur booster, the upper stage, that took it on out of the atmosphere of the Earth and then onto the moon. And then the two probes are right there underneath its fairing. So you can see the Centaur booster there, and it's a fairing probe underneath there. So that launched like a year and a half ago. Okay, go ahead. This is what it looked like when it was in space on its way to the moon. There's the Centaur, here's LRO, and here's the LRO probe. Now this is a diagram showing the trajectory. The green dot is kind of supposed to be the Earth, and then this blue thing is supposed to be the circular orbit of the moon, as seen from an oblique angle. And you can see they came out here and then took an abrupt turn. The turn is because the gravity of the moon. It swung around the moon. Now, well, two of them swung around the moon, the LRO and the Centaur. LRO separated before then and used its rocket engines to go into orbit around the moon when they passed the moon right there. So LRO went into orbit around the moon. LRO and the Centaur orbited the Earth 2 more times. And the reason they did this is to adjust the orbit so that they could come straight down into one of those polar craters and smash into the bottom of it. Now the Centaur went in first, and the LRO observed the impact of the Centaur. The Centaur, when they're out of propellant, the Centaurs weigh about 2 tons, and it was traveling about 5,500 miles an hour when it got to the bottom of the crater. And 2 tons at 5,500 miles an hour makes a pretty energetic impact. And that throws material off the surface, some of it going all the way up into the sunlight, where the reflected sunlight and also the emitted infrared radiation from that material can be used to analyze what's in it. So you can blast a bunch of stuff off the surface and look at the light off the plume to see what it's made of. That was the whole idea. So LRO followed the Centaur in, watched the impact, watched the plume get thrown up, and then itself was impacted, and its plume was observed by LRO. LRO also observed the Centaur plume. So go ahead. Here's a photograph, you can barely see here, of the plume taken by the infrared camera on board LRO. Minutes of the flight. It looks faint, but you look at the size scale here, 10 kilometers in diameter here. This is 20 seconds after the Centaur impact, so the plume has risen up into the sunlight, miles off the surface, and it's about 10 kilometers in diameter at that point. Okay, go ahead. And this is actually the crater produced by the Centaur, taken by the infrared camera on LRO before it impacted. Go ahead. And these are the basic results. So LRO had 2 spectrometers on board, which detect disease material. LRO had an instrument, has an instrument on board called LAMP, and it detects disease. So H2O, water, they found actually more than expected. So there's plenty of ice there. H2S, this is ammonia, sulfur dioxide, carbon dioxide, sodium, silver, and cyanide. LRO detected a molecular hydrogen, which was a surprise, nitrogen, carbon dioxide, sodium, mercury, zinc, gold, and calcium. Not sure what the implications of the gold are. It's interesting. But these were the materials that came up in the plume thrown out of the bottom of that crater. The main thing they were looking for is water, because that's the most valuable resource to them for a lunar base. Okay, go ahead. This is the LAMP instrument on board LRO that did the observing of the plume. Its main function in life, well, this was one function of that instrument, but its main function is to make images of the dark bottoms of these shadowed craters. Now you might say, well, they're dark, there's no light down there. Not quite, there's starlight down there. The stars are shining into the bottom of those craters, and they're faint, but this instrument is designed to make images in these extremely low light. There's also, in certain places, there's reflected light. Say you're in a dark bottom of a crater, but there's a crater rim that you can see from you that is in sunlight. So there's scattered light from there, not direct sunlight, but scattered light from the side of the crater and also starlight. So this instrument is building up images of the bottoms of these craters over multiple orbits. So it's still in the process. In fact, go to the next image. And this is the cumulative image taken by, so you can see there's not much detail so far in the bottoms of these craters. You can see a few little things. So, but as LRO continues to orbit, those images will slowly come into view of the bottom. So it's actually taking pictures of the bottom even though they're in almost complete darkness. Okay, good. So the whole thing was orchestrated, this impact was orchestrated so that LRO would fly over the impact site 90 seconds after the Centaur impact. And so here is the strip, the strip of temperature mapping made by the infrared diviner instrument. And you can see that they landed in a cold spot, purple cold spot, because that was the way it was planned. They figured the cold spot is where you're most likely to find ice, right? So they crashed in the cold spot, and you can't really see it here, but there's a tiny little white spot in the purple, and that's the warm area created by the Centaur impact. It's, I can only see it when I stand up here. And it's very tiny, but again, look at the size scale. So it's a pretty good size warm spot created by the Centaur impact. Okay, go ahead. This is a film of, if you put your cursor, I think it'll.
I don't know if it'll play, because it's not like PowerPoint where all the links are enabled.
Oh.
So we only see.
Oh, okay. All right. Well, it's a film from the infrared camera on board LRO, as it was sailing in toward the impact occurred right there, and you can see a little flash when the Centaur hits, and then it continues in, and you can actually see the glowing crater. This is an infrared image, so it wasn't glowing in visible light, but it was glowing in infrared because it was warmed by the heat of energetic impact. But you can follow it anyway. Nothing special. Okay, go ahead. Okay, this is the neutron detector. Neutrons are another way to look for water, and in fact, you can look for water underneath the surface. The reason there's neutrons coming up from the surface of the moon, go on ahead. The moon has no atmosphere, and so there are particles from outer space that strike the surface. Cosmic rays are mostly high-speed protons that come from other places in the galaxy. And they come slamming into the surface, and they might go into the surface before hitting an atomic nucleus. And then that process releases neutrons, and those neutrons can come spitting out, or they can rattle against other nuclei before coming back out. And if they hit most of the nuclei, they're silicon and oxygen, because that's what rock is made of. And those are, an oxygen nucleus is 18 particles in it, so it's relatively heavy, so when a neutron bounces off of there, it doesn't get nudged very much, and the neutron goes bouncing off without losing much energy. But if there's, say, a water molecule, and the neutron hits a hydrogen atom, the nucleus of a hydrogen atom is only one proton, so that really gets knocked a lot, and the neutron loses energy. So when you're in an area where there's water ice underneath the surface, the neutrons are going to come up at a slower speed, and there's also going to be fewer of them. So because of the fact that cosmic rays are constantly hitting the surface of the moon. If you point a neutron detector at the surface, the places where there's fewer neutrons coming up are places where there's lighter atoms, like hydrogen. Hydrogen-containing compounds, like water and perhaps ammonia. Go ahead. And this is a map made of both polar regions, and you can see this one's real obvious. There's a low neutron flux area at this crater called Shoemaker. And this is the place where the L-cross is floating. So, as you can see, a lot of areas around where there's low neutron flux. So this is a way to actually detect if there's water underneath the surface in a bunch of areas. Okay, go ahead. Here's this radio imaging experiment, and this is kind of an experimental instrument. Go ahead. This has created maps. These are maps of the polar region. I think this is the South Polar region, so you can see craters here. Go one ahead. This is a polarization map. There's something about it can measure radio polarization. That tells them something about the water that's on the surface. It's right on the surface. I'm not sure how much they've learned from just this instrument since it's like a demonstration. Okay, go ahead. Okay, now let me show you some photographs. This is a photograph taken from one of the cameras on board LRO, and not too many of them are taken at an oblique angle like this. Most of them are taken straight down, but this gives you a little perspective to include it. Go to the next one. In order to get a sense of scale, I found an object, a large object that's familiar to us, the Bank of America building downtown. That's the tallest building in Atlanta. It's 317 meters high. And go to the next. And I put it on this picture. There it is, right there.
Oops, what is it?
Oh, cool.
Where is it?
Right there. See that little?
No. Okay, so there is that.
So I scaled it down. And, I knew to scale this picture, so I scaled it down to the right side. I actually kind of thought it would be a little bigger than that. I scaled it down and just disappeared. So if they had built the Bank of America building on the rim of Cavius crater, this is where the L-cross crashed. That's what it would look like. With that nice view. So you can get a sense for the scale here. It's hard to get a sense of scale on the moon because there's no atmosphere and you don't see haziness for distant objects. So all the astronauts commented on that came back from the moon. They said they couldn't get any sense of scale. They look at a mountain they didn't know if it was 20 feet away or 200 miles. Okay, go ahead. Let me show you some other photographs. This is a photograph taken of an ancient crater called Menelaus, taken by the Apollo astronauts. And you can see during that impact, stuff was thrown out. This is called ejecta. And it's interesting to study this ejecta because it's material that's dredged up from underneath the surface. And that's what geologists want. One of the things that geologists want to see. But over time, it gets processed, chemically processed by sunlight. So if this happened 2 billion years ago, this stuff's been on the surface for that long, and it's heavily processed, plus it's been covered over by other stuff. Wouldn't it be nice to go down to this ejecta blanket, dig down, and find some of the stuff that was ejected back then, but not processed by the sunlight and buried by other stuff? Go to the next slide. Well, one of the things they do is they look at smaller impact craters that are more recent, that re-dredge the stuff up from the ejecta blanket of the big crater. So now the big crater dredged it up from maybe 5 miles underneath the surface. This one dredged it up 20 feet underneath the surface. It's much more recent. So this is a high-resolution image of a more recent impact crater, and this material comes from the ejecta blanket. This gives you an idea of some of the things that they do to study the geology on the moon from orbit. Good. Here's another impact crater. Hard to see it. You can see all kinds of rocks in here. These images are pretty amazing. I've never seen many pictures of the surface of the moon that had too many rocks on them, except pictures taken from the surface by the Apollo. But this resolution is so much better. And you can see material split down to the bottom of this bowl-shaped crater. Go ahead. Here's some volcanic domes. I'm not sure where these are, but this is caused by ancient volcanic activity, lava pushing up from inside, so that's why it's raised up. Go ahead. This is a feature that amateur astronomers like to look at. It's called the straight wall, or lupus recta. It's a tectonic feature, a split where the surface is displayed like that. It's not a vertical wall, but it's kind of a slope down like that. And this is just an image of it taken by LRO. Good. Here's a crater on the far side, King Crater, and you can see a number of interesting things. After the impact occurred, this is common for a crater, where material slumps down, the land slides down this way. This real smooth part, and that is solidified lava. A lot of times the impact of these things cause melting and causes the lava to flow to a place, and we call them lava lakes. So it looks like a little lake in there, because the lava flowed to that point and cooled. Good. Here's a place on the near side called Planet Iridium. Picture. So here, this was an ancient impact, and then volcanic activity filled it with lava, and you can see some impacts that have occurred since then. Good. This is a pit crater. These things are thought to have volcanic origin, but it's like it's almost like a room is under there, and there's a hole above it. So a number of these have been seen by LRO, and these are thought to be places where lava flows through some tunnels underneath the surface. And if they went there, they might be able to, lure somebody down there and walk through these tunnels and see where the lava flows early in the history of the moon. Good. These are probably volcanoes here. There's mounds, craters on the surface that are probably not impact craters, but volcanic calderas. So these are actual volcanoes, distinct volcanoes on the surface of the moon. Go ahead. Here, this is an impact crater that's very recent. It was caused by the Apollo 13 upper stage, called the Earth departure stage. It actually it's analogous to the Centaur stage. When they sent the Apollo missions to the moon, the last 5 missions, the upper stage that sent it there was purposely crashed into the moon. And that's because, not to look at the plume, but because it sent the big impact, it sent seismic waves through the moon, which could be picked up by the seismometers from the missions that had already been there. And that's, seismology is a way to study the inside of the planet, right? So they used the impact of the spent booster to do that. And this booster was much larger than the Centaur, but 7 times as heavy. So it was a more energetic impact. And it's interesting to see, you can see these older craters, these rays of material have since been processed by sunlight, and so they're no longer light. And so you can see the fresh craters, why it looks very different from the ones that have been there for millions of years. Good. This is hard to see. This is the Apollo 16 landing site. This is the descent stage of the lander that's still there. And some of these bright dots are the experimental things that they set up when they were there back in '72. And right around there, it's real dark in color because as they were walking around in their moon suits, they were kicking the soil up, and there was darker stuff underneath. This is, I don't know if you can see, but there's light-colored sort of strips going this way. They landed on the ejecta blanket of a large impact because they wanted to study that ejecta blanket. And so it's lighter in color, and as they shuffled around doing their work, they kicked up the darker material underneath, and that's why it looks so dark around the lander. But I wish you could see this better, because you can see individual footprint trails going out to these various things. I think this is the rover. They had a rover too that they went 20, 30 kilometers in, and there's footprints going out to it. So they've photographed all the Apollo landing sites, pretty high resolution. You can see everything they did.
See, we were there,
Yeah.
not a hoax.
And I think these were fake. So. Okay, go ahead. This is an interesting, it's an impact melt. See the way that it sort of looks like wax that's flowed out. Yeah, it's a rock that was melted by a large impact, flowed out and then solidified there. And I think I have one more impact melt. Good. Yeah, there's a thing too, but it's another impact melt thing with sort of big chunks that didn't melt. Looks like they went floating in and stuff. And it's not that far and solidified. So this is just a smattering of some of the pictures. Wow, so we're out of time. I was going to show you the website of LRO, because there's lots of pictures that they've taken, and some of them are really interesting things on the surface of the moon. This is the best photographic survey ever done of the moon, and they're discovering all kinds of things about the moon that nobody knew before. Well, there's a marker.
Oh,
Maybe not.
I believe.
But there's students waiting to get in here.
I think so.
Okay.
Yeah.
Well, if anybody's interested in that,
Well, you can send me the link and then I'll put it in the announcement of the archive.
okay.
I'll send it out by email. So
Okay.
we can do it that way.
Yeah.
Okay, so, well, let's thank our speaker real quick. And stay tuned, the next, popular STEM talk will be in January. So towards the end of January, I'll send out another, maybe biology, ecology, that type of thing.
Archive recording has been